A differential equation is simply an equation that contains a derivative. And while there are many different types of differential equations, we are going to be concerning ourselves with what we call separable differential equations in this course. That is to say, this equation can be rewritten so that we can separate x and y along with their respective derivatives on the different sides of the equation. And I'll talk about this in just a moment. And when we are solving a differential equation, what we're trying to do is we are trying to come up with the equation whose derivative is the dy dx or the y prime that's given in our differential equation. And we're going to be doing this in a couple of different ways, but know that first we will find what's called a general solution, which just effectively means a family of functions or family of curves, a family of curves. And these general solutions are going to be ones that have a constant of integration. And then we can use that general equation to find a particular solution, assuming that we are given some type of initial condition. Okay? So if you have a moment right now, pause the video right now and write down the steps that we have for solving differential equations. And once you have that done, let's actually go through this first example here together. So here's a differential equation. We got x plus 2y times y prime, and we're going to find the general solution of this equation. So the first thing we're going to do is we're going to rewrite this with our y prime rewritten as dy dx. And this will make a lot of sense in just a moment, but solving differential equations works a lot better when we rewrite our y prime as dy dx. Next, we want to separate our variables. So we're going to move that x over to the other side. So we're going to say 2y times dy dx is equal to negative x. Now to finish separating our variables, we're going to move all the variables together on one side so that y is with dy and x is with dx. And that's pretty easy to do here. We're just going to multiply both sides by our denominator. So we have 2y times dy is equal to negative x times dx. Okay, so we've successfully separated our variables. So hopefully now you see why it was so important for us to separate or to rewrite our y prime as dy dx. Now the next thing we're going to do here is we're going to go ahead and we're going to integrate both sides. And this makes a lot of sense because if we're trying to find the equation whose derivative is this dy dx here, okay, this dy dx here, the derivative, we're going to try to find the equation whose derivative is this dy dx, we've got to integrate both sides. So let's do that. So the left side is pretty simple to integrate. We've got 2y squared over 2, or just simplify to y squared. And the right side is going to be negative x squared over 2. Now, since we're integrating, we need to add some constant of integration. Now, you can add that constant of integration to either side. It doesn't really matter, but typically adding it to the side with dx, the side that's been integrated with dx, is going to make our lives a little bit easier. It's typically one less step. Because often we're going to be using this general solution to rewrite it as a particular solution. So having the c on the x side typically works better. So here is our general solution. We are done. If all we are asked to do is find a general solution, then here it is. This is our general solution here. Okay. So we've got a family of functions or curves. That is to say, we have an infinite number of equations whose derivative would be this dy dx, which in this case, we would say dy dx is equal to negative x over 2y, okay? Or would give us this original equation here. Now, a couple things that I want to highlight here. First off, I hope that we can see that this equation, that we were able to do this because we were able to separate our variables. An example of an equation that we don't really quite have the tools for doing yet in this course is a non-separable equation, such as something like dy dx is equal to x plus y. If you look at this carefully here, we see that there's really no easy way for us to group together our x's with our dx's and our y's with our dy's. All right. So now that we have our general solution, we will often use this general solution to come up with a particular solution. That is to say, I might give you some type of initial condition. Say x is this value and y is this value. What is the exact equation that goes through a particular point and has this derivative? Now, when we're doing something like that, in which case it might be a good idea for us to be able to rewrite this general equation explicitly. That is y as a function of x. In which case, if I wanted to write this as an explicit solution, I would say y is equal to the square root, or plus or minus the square root of negative x squared over 2 plus c. Okay, and we'll do an example of that in just a bit. All right, let's try another example of solving a differential equation then. Let's try something like number 2 here. Okay, all right, so the first thing that we're going to do here is we are going to separate our variables. So we'll say y minus 2, all of that times dx, is equal to x dy. Now let's move together our x's with our dx's. So 1 over x dx is equal to 1 over y minus 2 dy. Excuse me. All right, so now that we've successfully separated our variables, let's go ahead and let's integrate both sides. So integrating both sides now, the integral of 1 over x is just the natural log of absolute value of x. And let's actually add the plus c here. And this is equal to the natural log of the absolute value of y minus 2. Okay? Now we're going to go ahead and we are going to exponentiate both sides. That is to say, we are going to write both sides as powers of x. So let me take care of the right side first because it's first easier to see what we're doing here. E raised to the power of the natural log of the absolute value of y minus 2. Exponent properties say that e raised to the power of the natural log of some argument is just that argument itself. So this side would be absolute value of y minus 2. Now I'm going to do the same thing to my left side, but it's important to note here that I can apply the following log property, or the exponent property, I should say, that this is equivalent to saying e to the raised to the power of c. And in fact, let me call this c sub 1, because in a second you're going to see that that constant is going to change. Now, e raised to the power of some constant is just some other constant. So let's let c sub 2 be equal to e to the power of c sub 1. So e raised to the power of the natural log of the absolute value of x, this is just the absolute value of x. We're saying that e raised to the power of some constant is some other constant, which we're going to have to redefine as c sub 2. And this is equal to the absolute value of y minus 2. Now, since both sides have the absolute value, to rewrite this absolute value, we're splitting this up into two equations. That is to say, I can say the absolute value of y minus 2 is equal to, and let me just switch this around, c sub 2 times x plus or minus c sub 2 times x. And we're going to redefine this variable again. And you could have done this all in one step, but we're going to say let big C here be equal to plus or minus c sub 2. So that is to say, this final equation, y is equal to, instead of writing plus or minus c sub 2, we're going to write this as big C times x plus 2. And there's our equation here. Okay, where what's implied in here is that c could be equal to some constant. Now, if all I was being asked to do was find a general solution, then I could have stopped all the way back here, just at this step here. But if I wanted to find if I wanted to rewrite my general solution as an explicit equation, which we're going to have to do in just a moment, then this is how I would rewrite that step. Okay? All right, go ahead and try practice problems 1 and 3. And for these, don't worry about writing them as explicit equations. You can leave them as general solutions. All right, with that said, let's try a problem or an example where we're now going to find a particular solution as a function given some initial condition. So let's try number 4 here. Okay. All right, so for number 4, first thing we're going to do is we are going to separate our variables. So y times dy is equal to negative 2x times dx. Okay. And we're going to go ahead and integrate both sides now. So the integral of y dy equals the integral of negative 2x dx. So this is just y squared over 2. This is equal to negative x squared plus c. So from here, I am now going to use my initial condition here. I'm now going to use this initial condition. Now, you could continue to solve y right now as a function of x and then plug in our initial condition then. But typically for me, I find that it's a lot easier to start solving for c as soon as, no pun intended, as soon as I see it, as soon as it appears in my equation. So I'm going to plug in what we know. Our initial condition is effectively saying that at the point x, when x is equal to 2, y is equal to negative 4. So this is my initial condition. So let's plug in what we know. Y is equal to negative 4 squared over 2. X is equal to 2 squared, all of that plus c. So we have here, this is 16 over 2, which is 8. This is negative 4 plus c. So c is equal to positive 12. So now what we're going to do is we're going to insert that back in. We had our general solution here. This was our general solution. But now we're going to find our particular solution because we found the specific curve now that goes to the point 2, negative 4. So y squared over 2 is equal to negative x squared plus 12. So there's our not particle, that's particular. There it is. Sorry about my spelling. So now we have our particular solution, and we're going to finish this off by writing it explicitly as a function. So y squared is equal to negative 2x squared plus 24. And then we can say y is equal to plus or minus the square root of negative 2x squared plus 24. Now, when we look at this, we've actually got two equations here, but we know we only need one, or we can only have one. So this is where we go back to our initial condition. Note that here, when x is equal to positive 2, I go through negative 4. Therefore, this must be the negative equation there. That's the only way we would be going through negative 4 there. Okay. And you could actually try plugging in positive 2 there, and you would find that having that be negative is the only way we would get negative 4 as our output. Okay. So hopefully this helps help you understand kind of how to solve differential equations and the difference between finding general and particular solutions. Go ahead and work through the rest of these problems and check your solutions with what I have in Schoology.